Hello, my name is Chidamala Mechi and I study mechanical engineering. Today I will be discussing an article on flexion of the elbow, which was taken from Introductory Biomechanics from Cells to Organisms. Context. Background. The main purpose of the article is to examine flexion of the elbow in humans, focusing on how this flexion results in stresses on the forearm bones. There are three major bones in the arm. There is only one in the upper arm, known as the humerus, and two in the forearm, known as the radius and ulna, as you can see on screen. There are four main muscles which are responsible for flexion. The biceps. This muscle arises from 2 points in the shoulder blade, where the muscles then fuse together at these two locations to form the biceps and inserts into the radius. The brachialis arises from the humerus halfway between the shoulder and elbow, inserts into the ulna. The brachioradialis arises from the lower section of the humerus and inserts into the radius near the wrist. The extensor carpi radialis longus, ECRL, arises from the humerus near the elbow and inserts into the second metacarpal wrist bone. Objectives. Examination of the biomechanics behind elbow flexion, mainly the stresses flexion can cause to the bone of the forearm when holding a weight in the palm. Another aim is the deduction of the magnitude of the weight through application of equilibrium conditions for moment of interior. And finally, the calculations of joint reaction forces acting on the elbow in both the Y and X directions. Methodology. To find the weight of the object, equilibrium conditions have been stated for moment of inertia. As you can see, the weight acts in the negative Y direction. This results in a negative moment. But when the weight, along with its distance, is moved to the other side of the equation, it becomes positive, which can be seen in this equation over here. It's positive, but the weight in fact causes a negative moment. It's very important to note that the X component of the forces has not been considered due to the fact the X components of the forces do not in fact contribute to a moment. Forces have been summed together along with their distances to calculate the moment. LF is the distance between the center of rotation of the elbow and the insertion location, and theta is the angle the muscle makes with the horizontal forearm. And F is the force generated per unit PCSA. T1 to 4 is the resultant force from the biceps, brachialis, brachioradialis, and ECRL, respectively. The joint reaction forces in both the Y and X directions have been calculated through the application of equilibrium conditions. When finding JRFX, the weight has not been considered as it does not have a component in the X direction, unlike the muscles forces. And to find maximum stress, this is the application of this is the equation that has been used. The article relates to what was studied in both lecture 3 and 4. Lecture 3 focused on the theory of bending, which includes the assumption of equilibrium conditions for moment of inertia and forces in both the X and Y directions to calculate support reactions and loads. When stating equilibrium condition for moment of inertia, the moment is calculated using the equation moment equals force times distance. In our case, force is the resultant force of the muscles, and D is the distance between the center of rotation at the elbow and the respective insertion point of the muscle. In the article, the bone can be depicted as a beam with both the joint reaction forces X and Y, which can be depicted as reaction forces resulting from a pin support. Due to the fact a pin support produces forces in the vertical and horizontal directions, just like what is seen on the free body diagram. The last section of the article focuses on the stress produced on the bone. This relates to what was studied in Lecture 4, which discusses both the stresses and strains of a beam. As discussed previously, the bone can be interpreted as a Euler-Bernoulli beam. The same equation used to calculate stress on a beam is used to calculate the stress produced in the bone. Conclusion. The article successfully achieved its objectives by estimating stress and calculating JRF, while also acknowledging the limitations of its analysis, such as the simplifications made and the application of the Euler-Bernoulli's beam theory, even when the correct conditions have not been met for the application of this theory. Even with the identification of the limitations within the article, this does not take away from the fact that there is far too many assumptions made. Let's look at some of these assumptions. The first assumption made was that all muscles exert the same force F, which is actually not true because this force, which is the force per unit PCA, varies from muscle to muscle. Next is the simple assumption that the elbow can be interpreted as a simple hinge with reaction forces through the center of rotation is just simply unrealistic. A more complete analysis is required for more accurate results. For the application of the Euler-Bernoulli's theory, certain conditions must be met. Here are the following conditions which were not met. Constant and symmetrical cross-sectional area. The beam is to be loaded in its plane of symmetry. The material must be isotopic. And lastly, the plane section of the beam remains plane. To calculate stress, the bone has been remodeled in response to stress, and the radius and ulna were sized so that the predicted maximum stresses are equal, which invalidates the results achieved. The article also assumes that the medullary canal diameters are both the same for the ulna and radius at the point of maximum bending moment. This assumption determines the value of the inner diameter, which is an important parameter when calculating stress. The article fails to consider the force generated by the interosseous membrane. In conclusion, far too many assumptions have been made. Voice over simplification of conditions also, and many conditions required for the application of the Euler-Bernoulli beam theory have been ignored. Importantly, the Euler-Bernoulli theory should have been applied to only one bone. Instead it was applied to two. For this reason, the results should only be taken as a rough estimation. On the other hand, the article references other literatures and reports to validate their approximations, which indicates some level of accuracy within the results. Here are the references that I used. Thank you for watching.